Welcome to this problem walkthrough. In today's session, we'll be tackling LeetCode problem number 313, titled Super Ugly Number. This problem focuses on generating a sequence of numbers based on a given set of prime factors. It's a great exercise for understanding priority queues, dynamic programming, and efficient number generation. Let's dive in. In this problem, we are tasked with finding the nth super ugly number. Super ugly numbers are defined as positive integers whose prime factors are restricted to a given list of primes. The list of primes is provided in sorted order and contains unique prime numbers. For example, if the list of primes is 2, 3, 5, all super ugly numbers will only consist of these values as their prime factors. Importantly, the problem guarantees that the nth super ugly number will always fit within the range of a 32-bit signed integer. The input consists of two parts. First, the integer n, which indicates the position of the super ugly number we need to find. This value can range from 1 up to 100,000. Second, the primes list, which contains up to 100 unique prime numbers, each ranging between 2 and 1,000. The output is a single integer representing the nth super ugly number in the sequence. Let's look at an example to better understand the problem. Suppose we are given n equal to 12 and the primes list as 2, 7, 13, 19. The sequence of super ugly numbers generated from these primes is 1, 2, 4, 7, 8, 13, 14, 16, 19, 26, 28, 32. These numbers are formed by repeatedly multiplying and combining the given primes while maintaining ascending order. For instance, the first number is always 1, which is considered a super ugly number by definition. Then, the primes are systematically multiplied to generate the rest of the sequence. Here, the 12th number in this sequence is 32, which becomes our output. In another example, let's consider n equal to 1 with the primes list 2, 3, 5. In this case, the output is 1. This is because, by definition, the first super ugly number is always 1, regardless of the primes list provided. This rule applies to all inputs where n equals 1. The explanation for this is that 1 is the multiplicative identity, and it serves as the starting point for generating the sequence of super ugly numbers. No matter what primes are given, the sequence always begins with 1. Now, take the example where n is 15 and the primes list is 3, 5, 7. The sequence of super ugly numbers generated is 1, 3, 5, 7, 9, 15, 21, 25, 27, 35, 45. Here, each number in the sequence is a product of the primes from the list, combined in different ways and arranged in ascending order. For instance, 3 is the smallest prime, so it appears early in the sequence, followed by multiples of 5 and 7. The 15th number in this sequence is 45, which becomes the output. This demonstrates how the sequence evolves based on the given primes, and highlights the importance of efficient algorithms to handle larger values of n. There are constraints to keep in mind as we approach this problem. Specifically, n can range from 1 to 100,000, meaning we might need to calculate a very large number of super ugly numbers. The primes list can have up to 100 elements, and each prime is guaranteed to be between 2 and 1,000. Additionally, the primes list is always sorted in ascending order and contains unique values. Edge cases also play a significant role. For example, when n equals 1 and the primes list contains only 2, the output is 1, as the first super ugly number is always 1 by definition. Another edge case is when n equals 10 with a single prime, such as 2. In this scenario, the sequence consists solely of powers of 2, like 1, 2, 4, 8, 16, and the 10th number is 512. Lastly, consider a larger edge case where n equals 100 and the primes list is 2, 3, 5, 7, 11. Here, the sequence grows rapidly, and the 100th super ugly number will be a relatively large integer. Generating such a sequence efficiently becomes critical as the number of primes increases, and the value of n approaches its upper limit. A brute force approach would be too slow, so optimized algorithms, like using a min-heap, are essential to handle the constraints effectively. This ensures that we can generate and sort the sequence in a computationally efficient manner, even for large inputs like this one. When tackling the super ugly number problem, the brute force approach is the most intuitive starting point. The idea is to generate super ugly numbers by repeatedly multiplying previously found ones with each prime in the given list. While this method ensures that we eventually reach the nth super ugly number, it is computationally expensive. After generating all possible products, we need to sort the results and remove duplicates to maintain order. This sorting operation dominates the time complexity, making it n squared asterisk k, where n is the index of the desired super ugly number and k is the number of primes. Additionally, the space complexity is n, as we must store all the generated numbers. Ultimately, this approach becomes impractical for large inputs due to the inefficiencies associated with sorting and duplicate removal. To improve upon this, we can consider an optimized approach involving a min-heap. A min-heap, or priority queue, allows us to efficiently generate the smallest super ugly numbers in sequence. Instead of generating and sorting all possible candidates, we prioritize the smallest number at each step. The process begins by initializing a min-heap with the given primes. We then iteratively extract the smallest number from the heap, add it to our results, and push its multiples back into the heap. To prevent duplicates, we use a hash set to track numbers already present in the heap. This reduces the time complexity to n asterisk log n, where each of the n numbers requires heap insertions and extractions, each taking log n. The space complexity is n plus k, accounting for the heap and the hash set. While this method is more efficient than brute force, the trade-off lies in the additional memory overhead for the heap and hash set. Although effective, there is still room for improvement, especially in minimizing redundant computations. The dynamic programming approach offers the most efficient solution for this problem. The key idea is to directly generate the next super ugly number by leveraging the structure of the primes in previously computed numbers. We maintain an array of pointers, one for each prime, which tracks the current multiplier for generating new candidates. At each step, we calculate the smallest candidate by multiplying each prime with the super ugly number indicated by its pointer. This candidate becomes the next super ugly number, and we increment the pointer for the prime that produced it. Using this method, we avoid sorting and duplicate removal entirely. To implement this, we create a DP array of size n, where each index stores the corresponding super ugly number. Starting with DP 0 equals 1, we iteratively generate the next numbers until we reach the nth super ugly number. The time complexity is n asterisk k, as we calculate k candidates for each of the n numbers, and the space complexity remains efficient at n plus k. The dynamic programming approach stands out as the optimal solution for this problem due to its efficiency and simplicity. By avoiding costly operations like sorting and duplicate removal, it minimizes unnecessary computations and reduces both time and space complexity. The space requirement is n plus k, for the DP array and the pointers. This method directly generates the nth super ugly number in n asterisk k time, making it particularly advantageous for large inputs. Comparing the three strategies, the brute force method is simple but highly inefficient, especially for large inputs. The heap-based approach improves upon this with better time complexity but introduces additional memory overhead. In contrast, the dynamic programming approach strikes the perfect balance, offering an optimal solution in terms of both time and space. This makes it the most suitable choice for solving the problem effectively, even for large-scale scenarios. To solve the problem of finding the nth super ugly number, we focus on numbers whose prime factors come exclusively from a given list of primes. For instance, with the primes 2, 3, 5, the sequence of super ugly numbers starts with 1, followed by numbers like 2, 3, 4, 5, 6, and so on, all derived by multiplying the primes together in different combinations. The goal is to locate the nth number in this sequence efficiently. To achieve this, we use an optimized heap-based approach. First, we define the inputs. N represents the position of the super ugly number defined, and primes is the given list of prime factors. Next, we initialize our data structures. A min-heap is used to track the smallest candidate numbers for the next super ugly number, while a set ensures no duplicate numbers are added to the heap. We start the sequence with the number 1, which is universal as it doesn't contain any prime factors but serves as the base case for generating subsequent numbers. The choice of a min-heap is critical because it allows us to retrieve the smallest candidate number efficiently, with each retrieval taking log k time, where k is the number of elements in the heap. After initializing the heap and set, we begin the iterative process. The first step is to push initial candidates into the heap. These candidates are generated by multiplying each prime in the list with the first super ugly number, which is 1. At this stage, we also ensure no duplicates are added by checking the set. Once the initial candidates are prepared, we iterate n1 times. In each iteration, we pop the smallest number from the heap, which becomes the next super ugly number. This number is then multiplied by each prime in the list to generate new candidates. Again, we verify that these new candidates are unique before adding them to the heap and set. Finally, after completing n1 iterations, the top element in the heap represents the nth super ugly number, which we return as the result. This algorithm relies on several key insights to optimize performance. First, redundant computations are avoided by using a set to ensure that each number is added to the heap only once. This not only prevents unnecessary duplications but also reduces memory usage. Secondly, the heap itself is highly efficient for this problem. By always maintaining the smallest candidates, it eliminates the need for expensive sorting operations and ensures that the next super ugly number is processed in the correct order. Additionally, it's important to handle edge cases carefully. For example, if the list of primes contains only one prime, the sequence will consist of powers of that prime. Similarly, if n is 1, the result is always 1, as this is the universal first super ugly number regardless of the primes provided. The core data structures in this algorithm are the heap and the set. The heap stores the smallest candidate numbers for the next super ugly number and allows us to retrieve the smallest element in O log k time. This efficiency is crucial for maintaining the algorithm's performance as we process each number. The set complements the heap by tracking which numbers have already been added, ensuring uniqueness and preventing duplicate computations. When analyzing the algorithm's complexity, the time complexity is determined by the heap operations. Each insert and pop operation takes O log k, and we perform these operations for n numbers. Furthermore, for each number, we multiply it by m primes, where m is the size of the prime list. This results in a total time complexity of O n asterisk m asterisk log k. The space complexity is primarily driven by the heap and set, which together store up to n numbers, leading to an O n space requirement. To solidify our understanding, let's walk through an example. Suppose we need to find the 10th super ugly number, with n equals 10 and primes equals 2, 3, 5. We start with a heap containing just the number 1 and a set initialized to 1. In the first iteration, we pop 1 from the heap and generate new candidates by multiplying it with each prime, resulting in 2, 3, 5. These are added to the heap, which now contains 2, 3, 5, and the set is updated to 1, 2, 3, 5. Next, we pop 2, making it the next super ugly number, and generate new candidates 4, 6, 10. After adding these to the heap and set, the heap contains 3, 5, 4, 6, 10, and the set expands to include these new numbers. This process continues until we've identified the 10th super ugly number. After 10 iterations, we find that the 10th number in the sequence is 12. This implementation solves the LeetCode problem number 313 super ugly number using a heap-based approach to efficiently compute the nth super ugly number. First, the function nth super ugly number initializes a min heap to track the next potential super ugly numbers. Each entry in the heap is a tuple, value, prime, index, where value is the next multiple of a prime number. Prime is the prime factor being used. Index indicates the position in the result list, ugly underscore numbers, from which this value was derived. The heap is initially populated with prime, 1, for each prime in the input list primes, representing the first multiple of each prime. The heap is then transformed into a valid min heap using heap.heapify. The ugly underscore numbers list starts with 1, as the first super ugly number is always 1. The algorithm proceeds in a loop until ugly underscore numbers contains n elements. In each iteration, 1, the smallest value is extracted from the heap using heap.heappop. This ensures that the next smallest super ugly number is chosen. 2, to avoid duplicates, the extracted value, val, is added to ugly underscore numbers only if it is different from the last number in the list. 3. The next multiple of the prime is computed by multiplying the prime with the value at the current index in ugly underscore numbers. This new value is then pushed back into the heap with its corresponding prime and an increment index. The process continues until ugly underscore numbers has exactly n elements. Finally, the nth super ugly number, the last element in ugly underscore numbers, is returned. This algorithm ensures efficiency by leveraging the heap to always extract the smallest value and avoids recomputation of already processed values. The overall complexity is O, n asterisk log, k, where n is the desired position and k is the number of primes. This is much faster than a brute force approach for larger inputs. Here, we begin by importing the necessary utilities and defining our solution class. The method int superugly number takes two parameters, n, representing the position of the superugly number we want to find, and primes, which is the array of prime numbers. To efficiently manage the computation, we use a priority queue, or min heap, which will always give us the smallest value at the top. Each entry in the heap is an array containing three elements: the current value, the corresponding prime, and the index from which the value was derived. We initialize the heap with each prime number, setting its initial value to the prime itself, and its index to 1. We then create an array, ugly numbers, to store the sequence of super ugly numbers. The first super ugly number is always 1, so we assign that as the first element of the array. The main loop begins, where we iterate from 1 to n1. In each iteration, we extract the smallest value from the heap and process it. If this value is not a duplicate of the previous number in the ugly numbers array, we add it to the sequence. If the value extracted from the heap is a duplicate of the last number in the ugly numbers array, we adjust the loop counter by decrementing it. This ensures that we don't include duplicates in our sequence. Next, we calculate the next multiple of the prime associated with this value. This is done by multiplying the prime with the next number in the ugly numbers sequence, determined by the index. We then push this new value, along with the prime and the updated index, back into the heap. This process continues until we have found all n super ugly numbers. At the end of the method, we return the nth super ugly number, which is the last element of the ugly numbers array. This ensures that our solution is both efficient and avoids duplicates, leveraging the priority queue to maintain order. To solve this problem, we start by understanding that super ugly numbers are built using only the primes provided in the list, and the first super ugly number is always 1. For this example, we need to determine the 12th super ugly number using the primes 2, 7, 13, 19. First, we initialize a heap to efficiently track the next smallest possible numbers generated by these primes. Each entry in the heap is a tuple containing three values: the current value, the prime that generated it, and the index in the result list that this value is based on. Initially, the heap contains the first multiple of each prime, and we also initialize the result list ugly underscore numbers with the first super ugly number, which is 1. In the first iteration, we extract the smallest value from the heap, which is 2. This number is added to our result list. Then, we generate the next multiple of 2 by multiplying it with the next value in the result list, pushing the new tuple, for 2, 2, back into the heap. The heap is then updated to maintain its order, and we are ready for the next iteration. In the second iteration, the smallest value in the heap is 4. We extract it, add it to our result list, and push the next multiple of 2, which is 8, into the heap. The heap is updated as before to ensure it remains sorted. From here, the process is repeated for a total of 12 iterations. During each iteration, the smallest value from the heap is extracted, added to the result list if it's not already present, and the next multiple of its generating prime is pushed into the heap. By the end of 12 iterations, our result list contains the first 12 super ugly numbers: 1, 2, 4, 7, 8, 13, 14, 16, 19, 26, 28, 32. The 12th super ugly number is the last number in the list, which is 32. This is the final output for the example. Now let's look at another example where we are tasked to find the 10th super ugly number using the primes 3, 5, 7. Again, we start by initializing the heap with the first multiple of each prime, and the result list ugly underscore numbers begins with the number 1. The steps are the same. In each iteration, we extract the smallest value from the heap, add it to the result list if it's not already included, and push the next multiple of the extracted prime into the heap. For this example, after the first 3 iterations, the result list grows to 1, 3, 5, 7, and after 6 iterations, we have 1, 3, 5, 7, 9, 15, 21. Finally, after completing all 10 iterations, the result list becomes 1, 3, 5, 7, 9, 15, 21, 25, 35, 45. The 10th super ugly number is the last number in this list, which is 45. This is the final output for this example. Lastly, consider the example where we need to find the 5th super ugly number using the primes 2, 3. As before, we initialize the heap with the first multiples of these primes and set the result list to start with 1. During the first iteration, we extract the smallest value, 2, and add it to the result list. The next multiple of 2 is pushed into the heap. After 3 iterations, the result list grows to 1, 2, 3, 4. Continuing the process, after 5 iterations, the result list becomes 1, 2, 3, 4, 6. The 5th super ugly number is the last number in this list, which is 6. This concludes the example and demonstrates how the algorithm efficiently calculates super ugly numbers by leveraging the heap to track and generate the next smallest values. To understand the time complexity of our solution, we need to break it down into its components. First, the heap initialization involves adding len, primes, elements to the heap. Constructing a heap of size k takes O, k, where k is the number of primes. Next, the main loop runs n 1 times because we start with the first super ugly number, which is always 1. During each iteration, the smallest element is removed from the heap, which is an O log k operation, and a new element representing the next multiple of a prime is added to the heap, which is also O log k. Together, each iteration takes O log k plus O log k, or simply O log k. Multiplying this by the number of iterations, n, the total cost for heap operations becomes O n asterisk log k. Finally, duplicate checking is done by comparing the current value being inserted to the last value in the ugly underscore numbers list. This comparison is constant time, O1, and does not affect the overall complexity significantly. When we combine all these components, we see that the time complexity is dominated by the heap operations. Therefore, the overall time complexity of the solution is O n asterisk log k, where n is the number of super ugly numbers we need to generate, and k is the number of primes. Now looking at the space complexity, the heap is a key contributor. At any given time, the heap contains at most k elements, which requires O, k, space. Additionally, the ugly underscore numbers list stores the first n super ugly numbers, which takes O, n, space. When we add these together, the total space complexity becomes O, n plus k. This balanced approach ensures that the solution remains efficient in both time and space. To better understand the efficiency of this method, let's compare it to a brute force approach. In a naive solution, we would generate all multiples of the primes, sort them, and then pick the nth smallest unique value. This is highly inefficient. Generating all multiples would require significant space, and sorting these values would cost O, m asterisk log m, where m is the total number of multiples generated. By contrast, the heap-based solution is far more efficient because it focuses only on generating the required values. It pushes only the next multiple of the smallest current value, avoiding unnecessary computations. The heap size remains small, with at most k elements, which minimizes both time and space usage. For best, average, and worst cases, the algorithm consistently performs O, n asterisk log k, operations, whether n and k are small or large. Even in the worst case, it remains far superior to the brute force alternative. The mathematical basis for the time and space complexity further reinforces the efficiency of this solution. The term n asterisk log k arises because heap operations, which include both push and pop, are O log k, and these are performed n times, once for each super ugly number. The space complexity, O, n plus k, is derived from the ugly underscore numbers list, which requires O, n, space to store the results, and the heap, which takes O, k, space for the k primes. Together, these complexities demonstrate that the heap-based solution balances time and space effectively. By selectively generating only the necessary values and maintaining a small heap, the algorithm ensures optimal performance for this problem. When working with the super ugly number problem, there are some common mistakes to watch out for. One of these is failing to handle duplicates correctly. If duplicates aren't filtered out when generating new super ugly numbers, it can lead to redundant computations and even incorrect results. To avoid this, you should use a set or a priority queue, which ensures that only unique numbers are considered. Another common issue is relying on an inefficient brute force solution. This happens when all possible numbers are generated, and each one is checked to see if its prime factors belong to the given list. This approach quickly becomes computationally expensive and doesn't scale well for larger values of n, like 10,000. Instead, a more efficient method involves using a min-heap to dynamically build the sequence. Lastly, there's the mistake of not accounting for multiple prime factors. For example, numbers like 6, which is the product of 2 and 3, demonstrate that a number can include more than one prime factor from the list. The solution here is to multiply all primes with the existing super ugly numbers to generate new candidates systematically. Another potential pitfall is improper heap initialization. If the heap is not initialized correctly, or if the number 1 is left out as the first super ugly number, the sequence will be incorrect, and your output will be wrong. Always remember to initialize the heap with 1 as your starting point, as this serves as the base case for generating subsequent numbers. Additionally, edge cases are easy to overlook but can create significant problems. For instance, what happens if the list of primes is empty, or if n is very small? Failing to account for these scenarios could lead to runtime errors or unexpected results. To address this, validate the input before processing to ensure the program handles these special cases correctly. In interviews, understanding the dynamic generation process is often emphasized. Rather than generating all numbers within a fixed range, a priority queue or min-heap can dynamically produce the next smallest super ugly number. This method is not only efficient but also prevents unnecessary calculations. While the heap-based approach is popular, dynamic programming with multiple pointers is another option. The trade-off here lies in implementation complexity and memory usage. A heap is typically easier to manage but uses additional space, whereas the pointer-based method can be more memory efficient but requires careful indexing. Interviewers may also ask about prime factorization and how it impacts the algorithm. Knowing why duplicates must be avoided and being able to explain how prime factors are used to generate new numbers is crucial. Optimization is another key focus. You should be prepared to discuss how the heap's insert and extract min operations work and their logarithmic time complexity. Finally, related problems like ugly number 2, ugly number 3, and group anagrams are great practice for understanding efficient generation and ensuring uniqueness. When exploring alternative approaches, the heap-based method stands out for its efficiency in dynamically generating numbers. It avoids the need to pre-compute large ranges, making it well-suited for larger inputs. However, it does require extra space for the heap, and its implementation can be slightly more complex. On the other hand, the dynamic programming approach with pointers is more space-efficient and may feel simpler for some developers. That said, it relies on managing multiple pointers and can be prone to off-by-one errors, so attention to detail is critical. Finally, while the brute force method is straightforward and easy to grasp, it falls short for larger inputs due to its inefficiency. It's important to choose the approach that best matches the problem's constraints and input size, while also considering clarity and ease of implementation for the given scenario. Great job! To wrap up, we've explored an efficient way to solve the super ugly number problem using a priority queue. This problem is an excellent example of applying heaps and dynamic programming techniques to real-world constraints. If you enjoyed this video, don't forget to like and subscribe for more coding insights. Keep practicing, and I'll see you in the next session. That's the end of this tutorial. I hope you found this explanation helpful for understanding the solution to this LeetCode problem. If you enjoyed this content, please consider subscribing to the channel for more coding tutorials and solutions. Feel free to leave a like if this video helped you, and don't hesitate to comment with any questions you might have. Thanks for watching, and happy coding!